Introduction. In the previous chapters, we have studied about electromagnetic radiation and its interaction with Earth's surface and the atmosphere. We also discussed about the diffraction, reflection, scattering, absorption and transmission of electromagnetic radiation. As we have learned that different Earth features display different spectral behavior depending upon the interaction with the electromagnetic spectrum. This interaction gives the information about the differentiation of the objects on the Earth's surface. In this chapter, we will discuss about the spectral properties in signatures of common Earth surface materials such as vegetation, water, soil, minerals and rocks. Spectral signature. Various remote sensing sensors are used to record the emitted or reflected electromagnetic radiation from various components of the Earth's surface. There are two observations on which the remote sensing system is involved. These are visual and spectral measurements. The visual observation involves observations such as color, shape, size, texture and temperature of an object of interest. Spectral observations involves measurement of spectral reflectance of a particular object in an institute using specially designed equipment for this purpose. Spectral signatures are the combination of reflected, absorbed, transmitted or emitted electromagnetic radiation by objects at varying wavelengths which can uniquely identify an object. The intensity of the refractor radiation or the reflectance in percentage of electromagnetic radiation coming from the material is plotted over a range of wavelength. The connected points produce a curve which is known as spectral signature of the material, or in other words, spectral response curve. The spectral signature is important for understanding of different terrain features such as water, rock, soil, vegetation, which interact with different beams of electromagnetic radiation. The spectral signature of an object is mainly formed due to the interaction between the electromagnetic radiation and the part of electromagnetic spectrum in which they are interacting. Heated, the energy reflected back from the object is measured by instrument such as task-specific spectrometer. All spectral reflectance state are unique to the material and the environment in which they are measured for. Example, mineral or rock signatures are vary with sample to sample, whereas the vegetation is even more variable as they are dependent upon the growth stage, health, moisture content. Spectral signatures can be characterized as spectral variation, where the variation is based on the reflectivity and emissivity as a function of wavelength. Second, spectral variations of reflectivity and emissivity with special position, that is with respect to size, texture and the size of the object. Temporal variation, the variation of emissivity and reflectivity like diurnal and seasonal cycle. Polarization variation, it was introduced by the material in the radiation, reflected or emitted by it. Each of these features of electromagnetic radiation may be interdependent, that is, the shape may be different at different times in different spectral bands. A measure of these variation and correlation between them with unknown features of an object provides the signature of the object concerned. The knowledge of the state of polarization of the reflected radiation in addition to the spectral signature of various objects in remote sensing dimensions for analyzing and interpretation. Remote sensing with these parameters are extremely useful in providing valuable data for discriminating the object. The spectral response of various land cover features. Spectral reflectance and spectral signature of vegetation. Spectral reflectance of vegetation over electromagnetic spectrum depends upon three major factors: pigmentation, physiological structure, the leaf moisture content. Effect of pigmentation absorption. We have already learned that vegetation appears to be green in color as it reflects the green light and absorbs red and blue of the electromagnetic spectrum. And in the case of vegetation, the reflection of green light is due to the presence of the chlorophyll pigment in the plant leaves Presence of the chlorophyll pigment results in unique spectral signature of vegetation that enables us to distinguish it easily from other types of land cover features in an optical or near-infrared image. The reflectance of vegetation is low in both blue and red regions of the electromagnetic spectrum due to the absorption of the red and blue wavelengths by chlorophyll for photosynthesis. It has a peak reflectance at the regions of green, which gives a green color to the vegetation. The reflectance of the vegetation changes according to the composition, maturity, the health of the vegetation. The amount of chlorophyll content determines the health of the vegetation. Chlorophyll strongly absorbs radiation in the red and blue wavelength but reflects green wavelength. Leaves appear to be green to us when chlorophyll content is maximum. In certain seasons, there is less chlorophyll in the leaves, so there is a less absorption and proportionately more reflection of the red wavelength, making the leaves appear red or yellow. Effect of physiological structure of the leaves. The internal structure of the healthy leaf acts as an excellent diffuse refractor of near-infrared wavelength. If we are supposed to be sensitive to the near-infrared, then trees would appear extremely bright to us at these wavelengths. In fact, measuring and monitoring the near-infrared reflectance is one of the ways by which scientists can determine how healthy or unhealthy the vegetation is. The shape of the reflectance spectrum varies with the type of education. For example, the reflectance spectra of deciduous and coniferous trees can be distinguished based on the reflectance spectrum periodicity used in coniferous trees have almost similar reflectance in visible region, but they vary in near-infrared region where deciduous trees have higher reflectance than coniferous trees. Reflectance spectrum also depends upon other factors such as leaf moisture, content, physical, chemical characteristics and health of the plant. The combined effects of leaf pigments in physiological structure give all the healthy green leaves characteristics reflecting property as a low reflectance of red and blue light, medium reflectance of green light and high reflection of near-infrared radiation. The major difference in the leaf reflectance between species depending upon leaf thickness, which affects both pigment content and physiological structure. For example, a thick wheat flat leaf will tend to transmit little and absorb more radiation, whereas a flimsy lettuce leaf will transmit much and absorb little radiation. The diagram shows the spectral reflectance of the leaf. Effect of leaf moisture. Leaf reflectance is reduced as a result of absorption by three major water absorption bands that occur near wavelength of 1.4 μm, 1.9 μm and 2.7 μm, and the minor water absorption bands at the occur near wavelength. The reflective of the leaf within these water absorption bands is negatively related to both the amount of water in the leaf and the thickness of the leaf. However, water in the absorption also absorbs radiation in these water absorption bands, and therefore the majority of the sensors are limited to the 23 atmospheric windows that are free of water absorption at the wavelength of 0.32 to 1.3 μm, 1.5 to 1.88 μm and 2.02 to 2.6 μm. Unfortunately, within these wave bands, electromagnetic radiation is still sensitive to leaf moisture. There are other effects on the spectral signature of the plants which include the soil background, vegetative, sensient, canopy geometry, phenology, etc. Spectral characteristics of vegetation. The spectral reflectance of vegetation can be detected in the following three major regions of electromagnetic spectrum. Visible region, where it is from 400 to 700 nanometers. Low reflectance absorption and minimum transmission is observed in this region regarding the vegetation. The fundamental control of the energy matter interaction with the vegetation in this part of the spectrum is plant pigmentation. Near infrared. The spectrum from 700 to 1315 nanometers, where high reflectance and transmission come very low absorption has been observed by the vegetation, and the controlling factors in this region are the internal structure of the leaf. Middle infrared. The spectral wavelength from 1350 to 2500 nanometers. As wavelength increases, both reflectance and transmission generally decreases from medium to low, while absorption increases from low to high. The physical controlling factor in the middle infrared wavelength for vegetation is in vivo water content. Spectral signature of soil. We observe that the soil appears to be brown to the human eyes. Brown coloring of the product of the green and red electromagnetic radiation, such as the brown surfaces absorb more blue wavelength than either green or red wavelength. And we also observe that very little energy is transmitted through the soil. The majority of the index flux is absorbed or reflected. The technical term for these type of soils is single scatterer. In the case of soil surface, the level of reflectors gradually increases with wavelength in visible and near infrared spectral regions. The reflecting properties of the majority of the soil is similar, come up with a positive relationship between the reflectance and wavelength. There are some characteristics of the soil that determine its reflecting properties or moisture content, organic content, leaf texture, leaf structure, and iron dioxide content. These are all interdependent. We have observed that water is relatively strong absorber of all wavelengths, particularly those longer than the red part of the visible spectrum. Therefore, as the moisture content of the soil increases, the overall reflectance of that soil tends to decrease. The soil rich in iron dioxide reflects proportionately more of the red than other visible wavelength and therefore appears to be red to the human eyes. Sandy soil, on the other hand, tends to appear bright white in imaginary because visible wavelengths are more or less equally reflected. Slightly less blue wavelengths are reflected. It results in yellow color. According to Stoner and Bram-Graner, 1981, there are four most important characteristics of the soil that determine the reflectance properties. Soil moisture content, organic matter content, texture and structure, iron dioxide content. Soil moisture content. It has been observed that when the soil is having high amount of moisture, then the surface reflectance of the soil reduces at all visible wavelength. This type of behavior has been observed till the soil is attained saturation, where further addition of moisture have no effect on the reflectance. The reflectant or at near infrared wavelength is also negatively related to the soil moisture, as they increase in the soil moisture will result in decrease in the reflectance due to water and hydroxyl absorption features. The effect of water and hydroxyl absorption is more noticeable in clay soil because they have much bound water and very strong hydroxyl absorption properties. Organic matter content. The fine is one of the major reasons for the organic content where large amount of bacteria in different organisms thrive in the soil. The organic matter of the soil is usually darker in color and its presence will decrease the reflectance from the soil up to the organic matter content of around 4 to 5%. When organic matter content of the soil is greater than the 5%, then the soil appears to be black and any further increase in the organic matter will have little effect in the reflectance. Texture and structure. Texture is nothing but how the soil is made up, either sandy or it may be clayey particles, and the structure is nothing but how they are being aggregated, for example, coarser grains, fine grains, etc. The relationship between the texture and structure of the soil can be described with two contrasting soil types. Clay soil, which have strong structure which leads to a rough surface on the ploughing, causes small shadow and lowering reflectance values. In contrast, sandy soil exhibit weak structure which leads to fairly smooth surface on ploughing with few shadows. It should be noted that the effects of the soil structure complement other properties such as low moisture and organic matter content to increase the level of sandy soil's reflectance. Iron dioxide content. Iron oxide gives a rusty red coloration to many soils by coating or staining individual soil particles. Iron oxide selectively reflects red light and absorbs green light. This effect is so pronounced that scientists used the ratio of red to green reflectance to locate iron deposits. Spectral signature of water. Majority of the electromagnetic radiation falling on the water are not reflected but either absorbed or transmitted. When the spectral signature is observed at the visible wavelength of the electromagnetic spectrum, small amount of the energy is absorbed, where in about 5% of the energy is reflected and the rest amount is transmitted. As you already know, the water is transparent to light to certain depth. We can observe that the things in clear water with our naked eye. Water in the near-infrared wavelength absorbs large amount of wavelength, whereas very little is left for reflectance and transmission. When compared to the soil, the water is more homogeneous. We can see the difference in reflectance of water, which is mainly due to the depth of the water and materials within the water. Light penetrates up to 300 meters depth and clear water is more transparent compared to the muddy water. In shallow waters, some of the radiation is reflected not by the water itself but from the bottom of the water body. Therefore, in shallow pools and streams, it is often the underlying material that determine the water body's reflectance properties. Long wavelengths of visible and near-infrared regions of electromagnetic radiation absorb more by water than shorter visible wavelengths. Thus, water typically looks blue or blue-green due to the shorter reflectance at these shorter wavelengths and darker if viewed at red or near-infrared wavelengths. If there is a suspended sediment present in the upper layers of the water body, then this will allow better reflectance and a brighter appearance of the water. The apparent color of the water will show a slight shift to the longer wavelengths. Suspended sediments can be easily confused with shallow but clear water, since these two phenomena appear very similar. Chlorophyll in algae absorbs more of the blue wavelength and reflects the green, making the water appear greener in color in the presence of algae. The topography of the water surface, rough, smooth, floating material, etc., can also lead to complications for water-related interpretation due to the potential problems of the specular reflection and other influences on color and brightness. The three most common materials suspended in water are non-organic sediments, tannin, and chlorophyll or phytoplankton. Non-organic slit and clay increases the reflectance at visible wavelength due to the interaction with and scattering by soil-like particles. In agricultural scenes, the main coloring agent is tannin produced by decomposing humus. This is yellowish to brown in color and results in decreased blue or increased red reflectance. A good example of the effect of tannin can be found in streams that drain peat moorlands. Chlorophyll content must be high before changes in reflectance can be detected. Water bodies that contain excessive levels of chlorophyll have reflectance properties that resembles, at least in parts, those of vegetation with increased green and decreased blue and red reflectance. Spectral signature of minerals and rocks. Rocks, like soils, are single scatterer and exhibit relatively simple spectral properties. Unlike soils, rock reflectance is less dependent on water content and completely independent of the organic matter content, texture or structure. Rock spectral reflectance primarily depends upon their own mineral composition. The mineral reflectances measured in the laboratory show there are two sources of variation: the overall level of reflectance, the specific absorption features. Low reflecting minerals such as geotite and ore of iron have spectral properties similar to the soil surface. Low to moderate reflectance at visible wavelength, increasing to the NIR. High reflecting minerals such as quartz, that is the silicate mineral, and calcite, the calcium carbonate, exhibit almost uniformly high reflectance throughout the visible, near infrared and SWIR spectrum. Differences between high reflectance minerals occur at specific wavelength, and these absorption features are known as diagnostic absorption features. For example, the effect of carbonate on the reflectance of the calcite at 2.35 μm. Some of the most pronounced absorption features are associated with clay minerals, as clay such as chlorite, aluminium hydroxide silicate may be associated with the presence of precious metals. It was not surprising that the mineral exploration community were the drivers behind the decision to include SWIR waveband on Landsat TM sensor that measured the reflectance at 2.08 to 2.35 μm. They are now leading the way in hyperspectral remote sensing at these wavelengths. Unlike other minerals, the strength of the bonding between the clay particles and the water produces some absorption features at 1.4 μm and 1.9 μm. To find out more about the measurement and analysis of the rock mineral spectral signature in detail, you need to understand about the spectroscopy and the hyperspectral remote sensing. Finally, before summarizing the session, it is important to draw your attention to the information regarding the description of the spectral properties and signature of vegetation, soil, rocks, minerals and water surface, which are typically of mid-latitude temperate climate. Those who are living or working in other parts of the world may experience a different set of surfaces or different canopy types. For example, in arid and semi-arid regions, you will find land surface with low vegetation cover, plenty of rock outcrops and soil cover with green land surface rather than soil, exhibit the particular spectral characteristics with its mineral content. At higher latitudes, you may also observe snow or ice cover surfaces with exceptionally high reflectance. You must also be aware that the solar elevation is generally low and therefore objects cast longer shadows at higher latitudes. Summary: the spectral signatures are specific combination of reflected, absorbed and transmitted or emitted electromagnetic radiation at varying wavelengths, which can uniquely identify an object. Vegetation has a unique spectral signature that enables it to be distinguished easily from the other types of Earth surface features in an optical or near-infrared image. Vegetation can be easily identified in the near-infrared regions of electromagnetic spectrum. The shape of the vegetation reflectance spectrum varies with vegetation types, soil moisture content, physical, chemical characteristics and health conditions of the plant. Soil reflectance is high in near-infrared and SWIR regions of the electromagnetic spectrum. These signatures differ based on moisture content, organic matter, texture, structure and iron oxide content of the soil. Water has higher reflectance in visible region of the electromagnetic spectrum. Longer wavelength of the visible and near-infrared regions of electromagnetic radiation are absorbed more by the water than shorter visible wavelengths. Thus, water typically looks blue or blue-green. Rocks or mineral reflectance are completely independent of rock material, of organic matter content, texture or structure. Rock spectral reflectance primarily depends upon their own mineral composition. Low reflecting minerals such as geotite have similar spectral properties to the soil surface. High reflecting minerals such as quartz and calcite exhibit almost uniformly high reflectance throughout the visible, near-infrared and SW infrared regions of the electromagnetic spectrum. The spectroscopy and hyperspectral remote sensing technology are used for better understanding of spectral signatures of specific materials.